Hi, I'm Yushi, a master's student from Xi'an Jiaotong University in Suzhou, China. It's my pleasure to present my co-authors here to present our paper, Predicting Gaze-Based Target Selection in Augmented Reality Headsets based on eye and head endpoint distributions. Target selection is one of the most common and fundamental tasks in AR systems. Today's AR HMDs allow users to select virtual objects via handheld controllers or mid-air gestures. However, there are situations where a user cannot interact with the AR HMDs using controllers or gestures, because one of both their hands are occupied with other tasks, such as carrying tools or other items. Such cases would become common as AR-HMDs gradually become more incorporated into people's daily lives, in the same way as personal computers or mobile phones. With eye tracking capabilities increasingly integrated into AR-HMDs, gaze-based input can help solve this dilemma. It can complement hand-based selection approaches. Eye-gaze is generally fast, as it could scan a wide range of areas with little physical effort. It's also lightweight, and often indicates selection intention. However, gaze-based selection can often be inaccurate due to the noise pattern of gaze points and the limitation in today's tracking devices. There is now a viable solution to this dilemma. User behavior modeling is widely considered to be a valuable tool for gaining a deeper understanding of user decision-making process and behavior patterns. By utilizing probabilistic-based models, user behavior modeling can automatically assist it in target selection process to make it efficient and accurate. Based on this, we identified three research questions. First, how can prediction assistance to be provided in AR systems to help users with gaze selection? Second, how do interface features, like object size and distance, influence users' gaze selection endpoints? And third, how do input mechanisms, like the eye blinking and L type, affect users' gaze selection endpoints? Our research for answers to the three research questions led to the development of two models for gaze-based or gaze-enhanced target selection. One model consists only the eye endpoint when a user triggers a selection. The other model adds the head endpoint to provide additional information in addition to the eye-only model. The second model further explains how a user's head and eyes collaborate during the selection process. The two endpoint-based models describe the probability distribution of a selection point when a user triggers a selection input. As shown here, the orange scattered points show the eye endpoint, and the blue one represents the head endpoint. Based on our research, we hypothesize that the endpoint distributions of both modalities, including the eyes and the head, to be bivariate Gauss distribution. We also hypothesize that the different task factors, including target size and target distance, could influence the parameters of the distribution. The distributions are used by all models to predict the likelihood of selecting an object. The object with the highest selection probability will be chosen as the predicted target. The basic idea of our unimodal, the eye-only model, is to automatically select the target with the highest probability based on their gaze pointing direction once a user triggers a selection input. The concept is similar to previous works that leverage Bayes' theorem for target prediction. The most important parts are P brackets G given T, which is the likelihood of selecting a particular target T with gaze pointing direction G, which can be calculated based on the eye endpoint distribution probability density function. Our multimodal model further extends the unimodal by incorporating head pointing direction to determine the intended target of selection. In this case, the probability of selecting a target T with gaze pointing direction G and head pointing direction H can be expressed as P bracket T given G and H. Just like the unimodal, we can convert the multimodal into this equation. Here, we want to determine first, P bracket H given G. The probability of head pointing direction H given a gaze pointing direction G for a specific target. This can be calculated based on the relative probability distribution of the head by treating the gaze pointing direction as original for selecting a target. Second, P brackets G. The probability of gaze pointing direction G when selecting a target. Both terms can be determined from an empirical user study, where users would perform a gaze-based target selection on objects of different size and distance. After computing these values from the probability density functions, our multimodal prediction model can then pick the object with the highest P brackets G and H as the intended target. To build the models, we first conducted a data collection study to explore how factors including target size and target distance can influence endpoint distributions of users' eyes and head. Additionally, we investigated the two conformation mechanisms, the blinking and the L-tab, as they could result in different endpoint distributions. We adopted a similar approach to phase ring as in previous work. There were 21 virtual grid spheres in front of participants. In each trail, one sphere would turn blue, representing the target of that trail, and the participant needed to move gaze-based cursor to select it. If a target was selected, the next target would appear opposite to it, which yield a consistent movement amplitude for all selections. Our results show that the target width W, movement amplitudes A, and important conformation mechanisms CM all had significant effects on either centers or variants of the eyes or head and point distributions. According to these results, we fit the unimodal model and the multimodal model based on the bivariate Gauss distribution. In our second study, we modified the phase ring with 4 distractors surrounding an intended target according to previous work and compared 3 gaze-based selection techniques. Target selection with visual boundary criteria, which is the baseline. Target prediction with our unimodal model, and target prediction with our multimodal model. This would allow us to quantify the performance improvement brought by the prediction models. The final results show that our models significantly improve the accuracy of object selection for small targets, achieving nearly 61% improvement for target with visual width of 0.5 degree, and approximately 32 improvement for targets with a visual width of 1 degree. The results also indicated that the multimodal model based on the eye and head and point distribution achieved a similar performance as the unimodal model, with only the eye and point distribution. Thank you for watching. For more information, please refer to our paper.